Hi guys, in previous lecture we have seen Thevenin theorem, Norton theorem and some problem based on these two theorems. In Thevenin theorem we have taken the three cases. In case 1 we talk about when only dependent sources are present in the network, then how will I reduce the circuit in order to find the VTH and RTH. Similarly, in case 2 we have seen when only at least one dependent source and one independent source are present, then how to find the Thevenin equivalent. In this case we find VTH and ISC, then we find RTH is equal to VTH upon ISC. Okay, and we also derive the equivalent circuit of Norton theorem, Norton equivalent circuit, that is the source transformation of Thevenin theorem. Okay, and then we have seen the problem based on the Thevenin and Norton theorem. Now in this lecture we will see maximum power transfer theorem and the problem based on maximum power transfer theorem. Okay, well, the maximum power transfer theorem is used to transfer the maximum power from source to load when the load is variable. That means this theorem is applicable only when the load is variable. Otherwise, choose the minimum internal impedance of the source which gives maximum current through the fixed load. So for fixed load, we don't use maximum power transfer theorem. For variable load, it is applicable. Got it? Now it is applied only if the network is linear. Okay, and also it can be applied for both active and passive network. Like this is the features of superposition theorem. Okay, so in order to find the maximum power, we divide the network into three categories. Okay, in case 1, that is in categories first, we have taken one voltage source. Like any complex linear network, we can represent that network in terms of one voltage source in series with resistance. Got it? That is the Thevenin theorem. Means if I will get any complex network and I have to find the maximum power across load, then I will reduce that circuit in one voltage source in series with one resistance. So I am taking this, the equivalent circuit, Thevenin equivalent circuit, and I am connecting one load. Okay, in this case 1, load and series resistance, this is RTH or series resistance, both are resistive in nature. That means load is also resistive and series resistance is also resistive, and this type of circuit can be applicable for both AC and DC sources. Okay, now see in case 2. In case 2 we cannot use DC sources. Why? Because here impedance will come into the picture. Suppose in any network, if you are getting VTH as voltage source in any complex AC circuit, we can reduce that complex AC circuit into VTH and RTH, and that RTH or impedance known as ZS, series impedance, consists of resistance and reactance both. Similarly, load is also consisting of resistance and reactance, and series impedance also consists of resistance and reactance. Then how to apply maximum power transfer theorem in this case, we will see. Now see in case 3. In case 3, input source is AC, okay, in series with impedance ZS, which consists of resistance as well as reactance. Okay, now I am connecting purely resistive load. So these three cases we have to study in maximum power transfer theorem. In first case both are resistive, in second case both are having resistance and reactance, and in third case only series impedance have resistance and reactance while load is purely resistive in nature. Then we have to find the value of load for which maximum power transfer. Okay, let us see each case one by one. First I will take case 1. In case 1, any complex network can be reduced by one voltage source in series with one resistance. Okay, and we have to find for what value of RL the maximum power transfer to the load. Got it? So let us suppose current I is flowing in the circuit, which is given by I is equal to Vs upon total resistance, that is equal to Rs plus RL. Now we know power across RL is given by PL is equal to I square RL. Now put the value of I, you will get Vs square upon Rs plus RL का whole square into RL. So in order to get the maximum power, for what value of RL we will get maximum power? For this we have to differentiate the power with respect to load resistance. Then we have to find the value of resistance for which the source will supply maximum power. So differentiate this PL with respect to RL and equate it to 0. That means first find dP upon dRL. What is dP upon dRL? This is U by V form. So V into Rs plus RL का whole square into differentiation of U, that is the numerator. So I will get Vs square minus U into, that is Vs square into RL into differentiation of denominator, that you will get 2 into Rs plus RL. Now this is dP upon dRL. Now this equate it to 0. You will get RL is equal to Rs. Means if the load resistance is equal to internal resistance of the circuit, then the source will transfer maximum power to the load. So this is the condition for maximum power transferred to load. Now find the maximum power. We know that power, the equation of power is this. So for maximum power, RL must be equal to Rs. So put RL is equal to Rs, you will get PL is equal to Vs square upon 4 RL, that is equal to Vs square upon 4 Rs. Okay. Now you know the value of RL and you know the value of Rs, so you can find the maximum efficiency. Efficiency is given by output power upon input power. What is the output power? Output power is equal to I square into RL. This is out. We have to find the output across load resistance. So output power is equal to I square into RL. And what is the input power? Input power is equal to I square into RL plus Rs. So after putting RL is equal to Rs, you will get efficiency is equal to 0.5, means percentage efficiency is equal to 50%. Got it? So whenever in the circuit you will get only resistance and variable load, and you have to find the value of load for which source will transfer maximum power, then put RL is equal to Rs and then find the maximum power. Got it? Now see the case 2. In case 2, source is AC because of reactance coming into the picture, means this circuit consists of resistance, inductance or capacitance, means this may be RL circuit, RC circuit or RLC circuit. So any RL, RC or RLC circuit can be replaced by one voltage source in series with impedance. That impedance is known as ZS. This is the ZS and this is AC source. Okay. Now I am considering that I have my load which consists of resistance and reactance both. That means load is having impedance ZL. Okay. So in this condition you will have three cases possible when RL is variable and XL is fixed, means XL is fixed in load and RL is variable. Second case is when RL is fixed and XL is variable, means RL is fixed, this RL is fixed and XL is variable. And the third case when RL and XL both are variable. So we will find the condition for maximum power transfer by considering one by one. Okay, in case second A, what we have, only RL is variable and XL is fixed. So first find the formula of power in this circuit. Okay, what is the current flowing through this circuit? The current flowing through this circuit will be V, this is the RMS voltage, V upon impedance ZS plus ZL. So I will get RS plus RL whole square plus XS plus XL whole square under root. This is the current flowing through AC circuit. Remember, this is in rectangular form, so we have to take magnitude, and the magnitude will given by RS plus RL ka whole square plus XL plus XL ka whole square. Now calculate power. Power is equal to I square R. So power you will get V square into RL by RS plus RL whole square plus XS plus XL whole square. Power is given by I square into RL. See, active power, we are finding active power, not total power. Total power is given by I square into Z. Okay, but we are interested in finding active power. We are not finding reactive power. Since active power is only we use, that's why you are finding active power, which is given by I square into IL, and after putting the value of I am getting power equation this. Okay. Now see case 2a, only RL is variable and XL is fixed. Means in this case, in order to transfer the maximum power, we have to differentiate the equation of power with respect to the variable one. Okay, means we will differentiate power with respect to DRL and equate it to 0. First find what I am getting. See, this power is in U by V form, so differentiation of U by V is equal to V into V is denominator is RS plus RL का whole square plus XS plus XL का whole square. This is denominator into differentiation of first, that is U. Differentiation you will get V square minus U into differentiation of V, that is equal to V square into RL into differentiation of V. So this part will be 0 because it will treat it as a constant value, and you will get only 2 into RS plus RL. Now this equation equate it to 0 in order to find what value of RL the source will transfer maximum power. So after equating it to 0 and solving, you will get RL is equal to under root RS square plus XS plus XL का whole square. This is the value of RL at which the source will deliver maximum power when only RL is variable and XL is fixed. Okay, now put RL, the value of RL in power equation, you will get maximum power, and for finding the efficiency you have to find the output power upon input power. Definitely the efficiency here you will get less than 50%. Okay, only you have to remember this, that efficiency you are getting less than 50%. Okay, now see the case 2b, when only XL is variable and RL is fixed. In case first, RL is variable and XL is fixed. In case second, we are considering XL is variable and RL is fixed. In this case also, when you will find, then you have to differentiate with respect to what? With respect to RL or with respect to XL? See, here XL is variable, means we will differentiate the power equation with respect to XL and equate it to 0. Okay, so differentiate the power with respect to XL, V as it is, that is RS plus RL का whole square plus XS plus XL का whole square. This is my denominator into differentiation of numerator. Since numerator is constant, because XL is variable, RL is fixed, so numerator is constant. So the differentiation of constant you will get is equal to 0 minus, take it here, minus U into, that is V square RL into differentiation of V means this. Finally XL plus XL is equal to 0 means XL is equal to minus of XS. This is the condition. This at this value of XL, the source will deliver maximum power to the load. Got it? Remember this. Now see case 2C, when RL and XL both are variable. So this is the case of case 2C is the sum of case 2A plus case 2B. In case 2A, what we are finding? We are finding the value of RL while XL is fixed. In case 2B, what we are finding? We are finding the value of XL when RL is fixed. In case C, when both RL and XL are variable, then what I will get? RL is equal to under root RS square plus XS plus XL का whole square. This you are getting in case 2A. In case 2B, what you are getting? You are getting XL plus XS is equal to 0. So these two conditions must be satisfied. After equating equation 2 in 1, I will get RL is equal to RS and XL plus XS is equal to 0. So when both RL and XL are variable, then to transfer the maximum power from source to load, the value of RL must be equal to RS and the value of XL must be equal to minus of XS. Okay, means if the series impedance ZS is given RS plus JXS, then load impedance ZL must be equal to RS minus JXS, that is equal to conjugate of series impedance. Remember this. Now see case 3. In case 3, we have AC voltage source in series with impedance which consists of series resistance and series reactance, but load contains only resistance part, means load is purely resistive. So in this case, we have to find the value of RL at which maximum power transfer to the load. See, case 3 is similar to case 2A. In case 2A, if we put XL is equal to 0, then we will get case 3. If we will put XL is equal to 0, then we will get case 3. That means equation of RL in case 2A is given by under root RS square plus XL plus XS square. So if we put XL is equal to 0, then we will get the condition for transferring maximum power from source to load in case 3, that is equal to under root RS square plus XS square. So this much value of load resistance is required to transfer maximum power to the load. Now how to remember, since we have case 2A, case 2B, case 2C, similarly case 3 and case 1, so how to remember these all cases? And how to remember the value of RL? I am going to tell you one shortcut. See, in any circuit, if only RL is variable, okay, in any circuit if only RL is variable, then RL is equal to magnitude of constant. That means whatever the constant impedance present in the circuit, that we take the mode of that constant, that will give the value of RL. Okay, this will happen when RL is variable. If only XL is variable, then we get XL is equal to minus XS. Got it? And if RL and XL both are variable, then in this case RL is equal to RS and XL is equal to minus of XS. Overall series impedance, the conjugate of series impedance will be the load impedance. So remember this short trick. Now take one problem. In this problem, we have to find the maximum power transfer to variable load RL connected across AB. First, the load is variable and we have to find the maximum power transfer to this load. So, this is the linear circuit and we can replace the linear circuit in terms of one voltage source that is given by Vs or Vth, whatever you can say, and one in series with one equivalent resistance that is equal to Rs or Rth, and then we can connect the variable load across it, RL. So first find Vs and Rs or Vth or Rth. So we have to find the Thevenin equivalent of this circuit. Okay, how will I find? Since this circuit consists of two independent sources and there is no any dependent sources are present, that means we will find Vth and Rth directly. So let us find first Rth. For finding the Rth, what we have to do? We have to disconnect the load resistance and we have to find the Rth across AB terminal. That will give you the Thevenin resistance by short circuiting the voltage source and open circuiting the current source. So these two voltage sources short circuited. Okay. Now find Rth. Rth is equal to 5 in parallel with 20. These two are in parallel. Then in series with 4. That is equal to 8 ohm. So we have got Rth is equal to 8 ohm. Now find the Vth across this terminal. How will you find the Vth across this terminal? I will take this is plus and this is a minus. Since this is open circuited, so no voltage drop across this 4 ohm resistor, and I will apply KVL here. Then I will move from here. So minus Vth, then I will get minus 12, then I will get plus voltage across 20 ohm resistor that is given by Vr is equal to 0. So Vth is equal to minus 12 plus Vr. Now Vr is the voltage drop across 20 ohm resistor. Since there is only one loop, so no current will flow outside and the current is given by 20 divided by total resistance that is equal to 25. Hence minus 12 plus Vr is equal to 20 into I is equal to 20 by 25, that means 4 volt. Okay, means Vth I am getting 4 volt. So we have Rs is equal to 8 ohm and Vth is equal to 4 volt, and we are connecting variable RL. Now find the value of RL for which the source will transfer maximum power. I have already told you the shortcut, that is if only RL is variable, then RL is equal to magnitude of constant. That means here is constant only 8 ohm, that means RL is equal to 8 ohm, and the Pmax is given by Vs square upon 4 RL. You will get 1 by 2 watt. Let's move to another problem. This problem has been asked in IES 2011. Okay. In this case, we have to find the maximum power transfer through variable load RL. Means we have to find the maximum power. So before finding the maximum power, first we will reduce this complex circuit into VTH and RTH. Okay, after that we will connect RL and find the maximum power. Now in order to find the RTH, the current source must be open circuited and voltage source must be short circuited. So open circuit all the current source and short circuit all the voltage source. Means this is short circuited and this is short circuited. So find the equivalent resistance. Equivalent resistance will be given by 20 parallel with 5 you will get 4, 4 in series with 8 you will get 12, 12 parallel with 4, that means you will get equivalent 3, and now this 3 is connected in series with 4, so finally you will get RTH is equal to 7 ohm. Okay, now find VTH across this terminal. Okay, so here 3 independent sources are present and we have to find the VTH across this. How will I find? See, we will use source transformation method and circuit reduction method both. Okay, this current source, practical current source, can be transformed into voltage source, and now we will use here the circuit reduction technique. I have already given you the shortcut when I was teaching you the nodal. This much circuit is replaced by 100 multiplied by 5 divided by 25. One voltage source whose values is given by 100 multiplied by 5 divided by this resistance plus this resistance 25 in series with 20 parallel with 5, that you will get 4 ohm. Okay, after that now transfer this current source, practical current source, into voltage source. Since the direction of current is like this, means current will always flow from positive to negative, so the voltage source polarity will be like this in series with resistance 8 ohm. Okay, now this is parallel with 4 ohm and we have to connect the VTH. Then we have to find the VTH here. This is 2 volt, this is 4 volt, and the value of this voltage source is given by 8 multiplied by 2, that is equal to 16 volt. Now take the equivalent of 16 volt and 20 volt. Finally you will get 4 volt. The voltage across this plus minus V1 is given by total voltage V, that is equal to 4 volt multiplied by the resistance of that branch in which we are finding the voltage, that is 4, divided by total resistance, that is 4 plus 8 plus 4, that is 16. So I am getting 1 volt. Now VTH is equal to, apply KVL here. Since this is open circuited, so there will be no voltage drop across this 4 ohm resistor. So move anti-clockwise, you will get minus VTH minus 2 plus V1 is equal to 0. Hence VTH is equal to minus 2 plus V1, that is equal to minus 1 volt. Now draw the equivalent circuit having VTH plus minus 1 volt and this is RL. Okay, since I have considered the polarity of VTH from plus to minus, A is connected with plus and B is connected to minus, that's why I am getting minus 1. Okay, if I will reverse the voltage polarity like this, then I will get 1 volt. No problem, since there is no any dependent sources are present, that means this network is passive network, not active network. Okay, only and the VTH I am getting negative. Why? Because of the, I am considering that A is at high plus potential and B is minus potential, but actually the polarity of B is plus and polarity of A is minus, that's why you are getting VTH negative. So I will reverse the polarity, means I will consider B as a plus and A as a minus, that means VTH is equal to 1 volt. Okay, So what is the value of RL? RL is equal to RTH is equal to 7 ohm. Okay, and the maximum power transfer from source to load is given by, so you will get 1 divided by 28 watt. Let's see this problem. In this problem, one AC voltage source in series with impedance having 10 resistance part and J10 reactance part is connected with load. This is my load, and in this load only RL is variable. Okay, remember the shortcut which I have told you, that if only RL is variable, then for maximum power transfer RL must be equal to mode of constant. Got it? Hence RL is equal to 10 plus J10 minus J15 mode of this, that is equal to mode of 10 minus J5. You will get under root 10 k square plus 5 k square, that is 125 ohm. Now see this problem. In this problem, one voltage source in series with resistance and reactance is connected with load. This is load. Okay, and in this load only reactive part is variable and resistance part is constant. So remember I told you, when only reactive part is variable, then that reactive part plus inside XS must be equal to 0. XL plus XS must be equal to 0. That means what is XL? XL is minus J XC. What is XS? Plus J10 is equal to 0. That means XC is equal to 10 ohm. Find the value of R for MPT, maximum power transfer. See, in this inductor of 1 Henry is given, frequency is equal to 10 is given, means XL is equal to omega L, omega is 10, that means J10 ohm is given, and we have to find R for MPT. So I remember I have told you the shortcut. If only R is variable, here since only R is connected means this is variable, then R is equal to mode of constant, 10 plus J10, mode of 10 plus J10 is equal to 10 root 2 ohm. Now see this circuit. In this circuit it is saying what value of R will give maximum power across 3 ohm resistor, means this is 3 ohm resistor. Okay, and for what value of R the network will give maximum power across 3 ohm resistor, means here the load is 3 ohm and we have to find the maximum power across this resistor. Okay, and this resistor is constant, means load is constant. So here maximum power transfer theorem is not applied. Then what we have to do, we have to find the minimum impedance path which gives maximum current through the fixed load. So we have to find the minimum impedance path, means if R is equal to 0 ohm, then we will find the minimum impedance path through which current I will get maximum current. Got it? So in this case R is equal to 0 ohm is the answer, not R is equal to 6 ohm. Generally people say that if I will connect 6 ohm here, then equivalent will be 3 ohm and 3 ohm must be equal to 3 ohm, that means it will transfer maximum power, but that is not the case here because here load is constant. So that's all about this lecture. In the next lecture we will see reciprocity theorem, substitution theorem and Millman's theorem, and we will solve some problem based on this theorem. So if you are having any doubt, then you can put it in the comment below, or you can join our Facebook group for doubt solving. For new updates, please subscribe to this channel. Thanks for watching this video.